Hi statisticians, this lesson is on normal calculations. Let's get started. This is Jose Fernandez, who was a former pitcher in Major League Baseball. Fernandez was originally from Cuba. In interviews later in life, Fernandez described growing up in poverty in Cuba, often playing baseball with sticks and rocks as a child because he couldn't afford official equipment. When he was a young adult, after 3 failed attempts, he was able to successfully defect from Cuba, traveling by boat to the United States. On that last journey, he famously saved his own mother from drowning on the rough seas. With Fernandez and his family risking so much to come to the United States, once he arrived, he worked incredibly hard to become a highly successful baseball player. He worked his way up and eventually became the best pitcher on the Miami Marlins Major League Baseball team. He was known throughout the league for his cheery attitude, and he was wildly popular among the Cuban American fan base in Miami. But then, unfortunately, in 2016, tragedy struck. Fernandez died in a boating accident off the coast of Miami at the age of 24. This tragedy sent shockwaves throughout baseball, his team, and the city. But September 26th, the next day, the Marlins were scheduled to play a game against the New York Mets. And here are some somber scenes from the field that day.
Difficult day in Miami for Marlins fans.
For Marlins fans, even for Met fans, for baseball fans. Marlins Park. This about 3 hours ago, D. Gordon with Jose's glove and Jose Fernandez's cap and a baseball. Tonight, the Marlins will play a baseball game. Just 36 hours from learning that they had lost their ace.
I don't know how they're going to do it, but the Miami Marlins are going to play a baseball game against the Mets tonight. I was especially struck by the poignancy of the national anthem, a song we hear every day. But for a young man who risked everything to be a part of this country, it rang a...
By the time the game was over, it became known as the Marlins Miracle. Here's why. D. Gordon, one of Fernandez's best friends, was the first batter for the Miami Marlins. When he stepped up to the plate, he had not hit a home run all season, after over 300 at-bats. Then, in that first at-bat, he did this.
Gordon has started to look like the D. Gordon
of last year. Gordon to right. It's deep. And it's gone! D. Gordon has hit it out, and the Marlins have a 1-0 lead.
That special home run and that special moment became known as the Marlins Miracle. It made headlines across the country as the nation was inspired by D. Gordon's heroic hit. But here's the thing. If we look at the situation a bit more carefully, there may be another potential hero in this story, a hero that can only be revealed through the study of statistics. And that potential hero is this guy, Bartolo Colon, the opposing pitcher for the other team during D. Gordon's at-bat. So that raises our key question for today. What role did the pitcher play in making the Miami Marlins miracle? With that question in mind, let's move into our notes. We're going to cover two topics today, starting with using values to find proportions in normal curves. So let's talk about this pitcher, Bartolo Colon. At the time, he was 43 years old. He was loved by fans, players, and basically everyone who interacted with him. And he had an iconic nickname, which he fully owned and that he used to refer to himself, quote, Big Sexy. And here's a reason for that. Because at 43 years old, he was still making plays like this.
He's just keeping the ball away from Bohr the whole game. He wants to get it. There, ball. Behind the back flip, and he got him. Wow. It's so easy for Cologne right now that he's able to fix it. Oh my gosh. There's a bag of tricks. This man will live forever. Like Bob Cousy. He's almost as old as Cousy. He's smiling. He knew it. Unbelievable.
And also impressively, at 43 years old, Colon still threw very fast. Among first inning fastballs that he threw in that 2016 season, his average pitch speed was 89.4 miles per hour. To put that speed in context, that means that the hitter, standing 60.5 feet away from the pitcher's mound, only sees that ball for less than half a second of flight before it reaches them. It turns out that if you look at the distribution of speeds among all of Colon's first inning fastballs that he threw that season, they were well modeled by a normal curve, with a mean of 89.4 miles per hour and a standard deviation of 1.7 miles per hour. So, according to the empirical rule, about 68% of his first inning fastballs were between 87.7 and 91.1 miles per hour, or within one standard deviation of the mean. 95% of his fastballs were between 86 and 92.8 miles per hour, or within two standard deviations of the mean. And 99.7% of his fastballs were between 84.3 and 94.5 miles per hour, or within three standard deviations of the mean. So with this distribution, we can look at the question like this. What percent of his fastballs were 92 miles per hour or faster? As with all normal curve problems, to tackle this question, we should use three steps. First, draw and label the normal curve, then perform the calculations, and finally, answer the question in context. So, the first step when answering this question is to draw and label the normal curve associated with Colon's fastballs. And so we do that. And note that we've labeled that the normal curve has a mean of 89.4 and a standard deviation of 1.7. And we label the tick marks showing those standard deviation markings. So to answer the question, we need to find the proportion of fastballs that are at least 92 miles per hour. The phrase at least means that 92 is the least speed we are looking for. So we're looking for 92 miles per hour and faster. So we're trying to find the percent of his fastballs in that upper shaded area, or the probability that this random variable is greater than or equal to 92, which we write in this notation. Now that we have a good picture of what this question is asking, it's time for the calculations. And we see that 92 is not exactly a convenient number for our curve because it doesn't fall on one of our labeled tick marks. So what should we do? Well, when we're between standard deviations in our normal curve, it helps to find the z-score and then use technology to finish up the calculations. So we can see that 92 is more than one standard deviation away from the mean, but it's less than two standard deviations away. So we can see that 92 is in between these values here. To find exactly how many standard deviations away from the mean it is, we're going to calculate the z-score. Remember our formula for a z-score. So to find the numerator, we are going to start by plugging in the values that we know. Our data value is the 92 miles per hour, and we drop that in. The standard deviation and the mean are the models that we used when we made our sketch. So the mean is the 89.4 and the standard deviation is the 1.7. We plug those in and simplify, giving us a z-score of 1.53. This means that 92 miles per hour is 1.53 standard deviations above the mean. So using the z-score, we can try to figure out what percent of his pitches will be more than 1.53 standard deviations above the mean. And you can use this using your preferred calculator or software. Note that we have a short calculator video linked in the description of this video. You can use Desmos, NumWorks, TI, etc. And you should pause this video before proceeding and then come back to this video. So, as shown in your preferred calculator or software, you now know that there is 6.3% of the curve above 1.53 standard deviations above the mean. That should make sense. If you are between 1 and 2 standard deviations above the mean, that corresponds with what we know about the empirical rule. Recall from this value, 2 standard deviations above the mean is 2.5%. So a little bit more than that would be 1.5 standard deviations above the mean, and 6.3% is a little bit more than 2.5%. So that checks out in terms of making sense of the problem. Our final step is to give our answer in context. So in context, 6.3% of his fastballs were at least 92 miles per hour. That is pretty impressive. Now that we've looked at some of his fastest pitches, let's look at some of his slowest pitches. And that brings us to finding values from proportions. Specifically, we're going to answer this question. What speed is at the 5th percentile of his fastballs? That means we need to find the speed that's only at or above 5% of his pitches. First, as always, we're going to draw and label our curve. We're given at the pitch speed, and we're looking for the lowest 5%. We're labeling the pitch speed X since we don't know that exact value. And then we're shading the bottom 5%. We set up our unknown expression. So P for probability of capital X, that is our random variable, is less than or equal to, because we've shaded the bottom part. Lowercase x, that's the unknown value we're solving for, equals 0.05 because we're shading the bottom 5%. Just like we did before in the last problem, it's going to be helpful to find that z-score. So just as we did before, we're going to pause the video and use technology. Use that same link in the description of this video. Use your preferred technology, and we're going to find that z-score that corresponds to the bottom 5%, and then come back to this video once you have that z-score. So using your preferred technology, you found that the z-score corresponding to the bottom 5% is negative 1.64. And from there, we can use our z-score formula to find the missing x value. So using our z-score formula, we'll be able to plug everything in that we know. We know the z-score, we know the mean, we know the standard deviation. We do not know the data value. So we'll be solving for x. So we've got an equation, we've got one unknown value, we're solving for that unknown value. First, we need to undo the division by 1.7 by multiplying both sides of the equation by 1.7. Then we undo the subtraction by adding the 89.4 to both sides and solving for x, and we get 86.6 miles per hour. And finally, we answer in context. We say that 86.6 miles per hour is at the 5th percentile of Cologne's fastball speeds. So this means that an 86.6 mile per hour fastball is unusually slow for him. It's only faster than 5% of all of his pitches. Now, with that information in mind, let's re-watch the Marlins miracle clip again, but this time pay attention to this part of the screen, which shows how fast the pitch is.
Gordon has started to look like the D. Gordon of last year. Gordon to right. It's deep. And it's gone! D. Gordon!
So that pitch speed in the clip raises our discussion question for today. Here are the locations of all the pitches that Colon threw to D. Gordon in that 2016 season. And note that the pitches near the middle of the strike zone, or in towards the middle of the box shown here, are considered easiest to hit. This dot right here shows the Marlins miracle pitch, and it was thrown at 85.7 miles per hour. Given the location and the speed, Colon was asked in a post-game interview if he purposely threw an easy pitch. Colon ended the interview early and walked out. So this brings us to our discussion question. Do you think Colon purposely threw an easy pitch? Justify your answer using a normal curve calculation. And here's a hint to get you started. Using the normal model from this lesson, try to find the probability of him throwing a fastball that is 85.7 miles per hour or slower. So with this in mind, take a moment to jot down your response to this question, and we'll discuss it further in class. That's it for today's statisticians. We'll see you next time.